I'm looking at the practice exam for the final exam coming up. You'll notice a few differences in the instructions, one being that you have 120 minutes, full 2 hours to do this exam. The other thing is that you may use any of your notes on the final exam. And no limit on the notes. You can bring in as much as you want. Anything else? Oh, you will be given 10 problems and you must complete 8 of them. So we're just doubling the length of a normal test. You have 10 problems, you can skip 2 of them. All right, let's get started. So you are asked to sketch the position time graph for an object moving in the negative direction, first with fast constant speed and then with the slow constant speed. All right? So time is the horizontal axis and position, it's just one-dimensional position, so we'll say x is the vertical. Now the object is moving in the negative direction, so we assume that the object just starts here at the origin. Why not, right? You always choose your starting position to be 0. And it's moving in the negative direction, which means it must move down here, not up here, because it's moving in the negative direction. Now, what is the shape of this graph? Well, it's moving with fast constant speed. So we know that the line is going to be, I didn't curved it a little bit at the beginning. It should be a linear line because the speed is constant. That means with every amount of time that passes, you'll cover the same amount of distance. Now, fast, meaning that the magnitude of the velocity is high, meaning that the magnitude of the slope is high. So that is so there is a large rise over run. Now this is in the negative direction. So again, we're talking the magnitude or speed, not the total velocity. And then the second part, it moves with a slow. Let's put a little dot here to mark. This is part 1, and then in the second part moves with a slow constant speed in the negative direction. So you notice the slope is still negative. We're not moving back upward. We're still moving in the negative direction, but we're moving at a slower speed, which means a shallower slope. The slope of this part is actually greater than that part because it's less negative, but we're just looking at the magnitude here to find the speed. And so in terms of magnitude, this is a smaller magnitude than that. It's less negative. So now if we are to look at the velocity with respect to time, the velocity is just the slope of the position, or the derivative of the position. Since we're not dealing with continuous functions, we don't have to take the derivative or anything. But the slope of this line is a constant, and it is a negative constant since the slope is negative. So it'll be something like this up until that point. And at this point, the slope is going to be lower, but it's still constant, so it would be a negative line. It would be a constant value, still in the negative region, but lower magnitude, closer to the axis. Now, in the third part, we are asked to graph the acceleration. Well, if it's constant velocity or constant speed, then acceleration is just negative the whole time. Acceleration is 0 the whole time. A equals 0. Part 1, a projectile is fired from a gun. It has initial horizontal and vertical components of velocity equal to 30 meters per second, 40 meters per second, respectively. Determine the initial speed of the projectile. Well, we're given some velocity, v0, and we have v0x and v0y. We have these two components. So if we want to find the speed, the initial speed, v0, that is just going to be equal to v0x squared, the square root of v0x squared plus v naught y squared. Just Pythagorean's theorem. A, B, C. C equals the square root of a squared plus b squared. Okay, then so V naught is equal to the square root of 30 meters per second quantity squared plus 40 meters per second quantity squared. And if you do the calculation, that comes out to 50 meters per second. So in part B, see, this is part A. In part B, we are asked to find what is the angle measured with respect to the horizontal. So we'll just use tangent of theta equals opposite over hypotenuse, or in this case, we'll call this theta. Tangent of theta equals opposite B over adjacent. I think I said hypotenuse a second ago. In this case, that's the general form over here. In this case, the opposite is V naught y, and the adjacent is V naught x, the y component of the initial velocity and the x component of the initial velocity. And to solve for theta, we'll just use the inverse tangent function. And we'll put in our numbers in the y direction. It's 40 meters per second, and in the x direction it's 30 meters per second. You know, I didn't draw this to scale. It should not be more horizontal. It should be more vertical than that because the vertical component is larger. Sorry about that. But it's just a schematic. So theta is then equal to 53.1 degrees. Part C says approximately how long does it take the projectile to reach the highest point in the trajectory? Well, here's where it's a kinematics problem, so we'll list our kinematic variables, y0 equals 0, because that's where we're starting. Y equals, we don't know this, and I'll just sketch out the problem. The projectile goes up, and we're looking for the highest point. This is y0. Okay, Vy0, well that we are given, that equals 40 meters per second. And Vy is equal, well, since it's at the top, it's at the very highest point in the trajectory, that velocity equals 0. Because it's still moving in the x direction, but it's not moving in the y direction. And Ay is negative 9.8 meters per second squared. That's the acceleration due to gravity. Time is what we are after. Well, if you remember the simplest kinematic equation, or at least I think it's the simplest, Vy is equal to V naught y plus At. Well, like we said, that's equal to 0. So then T is equal to negative V naught y over A, which is equal to negative 40 meters per second over negative 9.8 meters per second squared. T is equal to about 4 seconds. Say it's about 4 seconds. This is part 2 of the problem. This is the same problem. We're just asked some different questions. So, you know, if on the test you had trouble with one of these, you could do the first part and skip this part, or vice versa. Okay, so you've got the same situation. V0x, V0y, V0. And we're asked what's the speed of the projectile when it's at the highest point in the trajectory. So if I draw a diagram, projectile goes like this, and we want to know what is the speed right there. Well, this is easy. This is a write-down, because at the highest point in the trajectory, its velocity is all horizontal. The y component of the velocity equals 0, so we'll say Vy equals 0, and Vx is just the same as it was in the beginning, V0x. And that is because the acceleration in the x direction equals 0. So right here, I can just write down that the velocity total velocity equals the x component of the velocity, which equals the original x component of the velocity, which equals 30 meters per second. So part B, what is the acceleration of the projectile when it reaches its maximum height right here? Well, we already said the acceleration in the x direction is equal to 0, so that means the acceleration is due only to the acceleration in the y direction, which is equal to negative 9.8 meters per second squared. Simple one there. And C, what is the magnitude of the projectile's velocity just before it strikes the ground? So that means right here. What is this velocity? Well, we know that Vx is going to equal the original component. What is Vy? Well, Vy, we know just from symmetry, is the negative of the initial velocity in the y direction. It initially has some component, Vy0. That gets smaller and smaller as it gets to the top. At this point, the velocity in the y direction is 0. Then it starts speeding up in the y direction as it comes down over here. And since it's the same amount of time up as down and the constant acceleration, then this component is going to be equal to the negative of this component. So Vy equals negative Vy naught. That means the total velocity is going to equal the square root of Vx squared plus Vy squared, which is going to equal the square root of Vx naught squared plus negative Vy naught squared. Does that negative matter? No, it doesn't, because square it, it goes away. But anyways, 30 meters per second squared plus negative 40 meters per second squared, quantity squared, excuse me. That's very important because we're squaring the negative as well. So V equals 50 meters per second. All right, so here we have a box of oranges. Keywords here, box of oranges slides from rest down a frictionless incline from a height of 5 meters. A constant frictional force is introduced at point A, and it brings the block to rest at point B, 19 meters to the right of point A. So part A says, what is the speed of the box just before it reaches point A? Well, this we can do with simple work energy considerations. We know H naught equals 5.0 meters and H final, called H final, equals 0 meters. The velocity in the beginning is 0 because it's at rest, and the velocity of the final is in question. That's what we're looking for. It is sliding. It is a box of oranges that are sliding, so there are no rotational considerations to take. You don't have to take any kind of rotational dynamics into account here. All we have to do is start with the work energy theorem, and we know it's a frictional plane, so this equals 0. It's a non-frictional, it's frictionless incline, so there are no non-conservative forces. The change of energy equals 0. So E initial equals E final, KE initial plus PE initial equals KE final plus PE final. All right, so 1/2 mv initial squared plus mgh initial equals 1/2 mv final squared plus mgh final. Well, we know that the final height is 0 and the initial velocity is 0. We have got two masses, the m's cancel out. So Vf is just equal to, bring the 2 over, 2gh naught square root, or square root of 2 times 9.8 meters per second squared times 5.0 meters. And when we solve it out, when we calculate everything, that comes to 9.9 meters per second. So we'll draw a line here. This is A. Let's go down to point B, or part B. What is the coefficient of kinetic friction of the surface from A to B? Well, let's draw ourselves a schematic. We have friction working in that direction, whereas the displacement is to the right. So that means the angle between the force and the displacement is 180 degrees. We'll have to keep that in mind. All right, so let's look at the work-energy balance. So the work from non-conservative forces is equal to the change in energy, which in this case does not equal zero because there is friction involved. Friction is a non-conservative force, and it's going to change the total energy of the system. So what does that mean? That means EF minus E initial does not equal zero. And we can expand this as KE final plus PE final minus KE initial plus PE initial. Now, the potential energy, it's moving along the point that we defined this level as zero potential energy, but even if we didn't define it as zero potential energy, whatever the potential energy at the surface is, it's the same in the final and the initial case, so these two are going to subtract out. We also know that kinetic energy is going to be zero at the end because, not at the initial, at the end. Because velocity equals zero at that point. Okay, so work non-conservative is equal to negative KE initial, which is negative 1/2 mv initial squared. Now, what is the work? Well, if you remember from the definition of work, that is the force involved, which in this case is friction, times d, the displacement, times cosine theta, where theta is the angle between them. Well, we said this is negative 1 because theta is 180, so negative FD equals, what's the negative out there, 1/2 mv naught squared. Negatives cancel. The force of friction we can then say is equal to mv naught squared over 2d. Just the algebra here, I'm solving for the force of friction. Oh, I forgot one more thing. The force of friction is equal to mu sub k, kinetic energy, times the normal force. Well, the normal force is just equal to mg because it's a horizontal plane. So Fg equals Fn, where Fg equals mg. Now, if this were not a horizontal plane, if this were a tilted plane, that would not be the case. But since it's horizontal, we can say we can say that the normal force is equal to mg, and that makes the m's cancel, and so mu sub k is equal to v naught squared over 2gd. What is v naught squared? That's a question. Well, v naught squared is actually the final velocity from the previous part because the block falls down this incline, gains speed until its final velocity at point A is the initial velocity when we're looking at this part of the problem. So that just equals 9.9 meters per second quantity squared over 2 times 9.8 meters per second squared times 19 meters. And when you do the math, that comes out to 0.3. It's a coefficient of kinetic friction, excuse me. All right. Okay. We have here a 325 Newton force that it accelerates a 50 kilogram crate from rest along a horizontal frictionless surface for a distance of 20 meters as shown in the figure. What is the final speed of the crate? Well, this is very similar to the problem we just worked. So force applied equals 325 newtons, mass of the crate equals 50.0 kilograms, and the displacement equals 20.0 meters. Part A says, what's the final speed of the crate? Well, we'll use work non-conservative is equal to change in energy, the work energy theorem, and we know this does not equal 0. We have a non-conservative force, which is this 325 Newton force. That is going to do some work. How much work? Well, that's equal to FA times the displacement times cosine of the angle between them. Well, the displacement is in this direction. The force is in this direction. So the angle between them, theta equals 0. And cosine of 0 equals 1. So that's going to equal the change in energy, which is just like we did before, KE naught plus PE. I'm sorry, it's final, excuse me. Minus KE naught plus PE naught. Okay, well, the potential energy, no matter what it is going to subtract out because it's the same. It does not change because it's not gaining any altitude. We also know that it starts from rest, so the kinetic energy in the beginning is equal to 0. And so all of this is just equal to KE final, which is equal to 1/2 mv final squared. So right again, FAD is equal to 1/2 mv final squared. And what's the final speed of the crate? Okay, so we'll solve for VF. So VF is equal to 2FAD over m and the square root of the whole thing, which equals square root of 2 times 325 newtons times 20.0 meters over 50, oops, not 5, 50.0 kilograms. Plug that in your calculator. The final velocity is 16.1 meters per second. So part B, how much work is done on the crate? Well, that's easy after doing the first part because the work is just, well, write it out. Equals FAD cosine theta, where we said the theta equals 0 degrees, so cosine of 0 is 1. So the force is 325 newtons times 20.0 meters. And the work done then is 6,500 joules. Part C. What coefficient of friction would be required to keep the crate moving at a constant speed under the action of the 325 Newton force? Okay, so we're applying the force, and up until now it's been frictionless. We haven't, dealt with friction. But now this question states that the crate is moving at the speed of 16.1 meters per second. Now, it's not a crate. It is a crate, sorry. It's moving at 16.1 meters per second. What kind of friction are we going to have to introduce to keep it moving at that same speed, constant speed? Well, what does constant speed mean? Constant speed means acceleration equals 0, which means F net equals 0. So we have a crate moving along, we've got the force applied, we've got force of friction, we've got force of gravity, and we have the normal force. All these forces have to cancel out. So we know that it's going to cancel out in the y direction because the crate's not floating or sinking. But the sum of the forces in the x direction is going to be Fa minus force of friction, and that's going to equal Max, which equals 0, because it's moving at a constant speed. So Fa equals the force of friction, and that is equal to mu sub k times Fm. Again, that's kinetic friction because it's moving, equals mu k Fg, because Fn minus Fg equals 0. That's the sum of the forces in the y direction. So Fn equals Fg. And we know that Fg is equal to mg. So then mu sub k is equal to Fa over mg. And mu sub k is equal to 0.7. Okay, so block A has a mass of 10 kilograms, and it rests on a 35-degree incline. Coefficient of static friction is 0.4. It's attached to a spring that passes over a massless, frictionless pulley at the top. What does that mean? That's very important. That means the moment of inertia is going to equal 0. So there is no rotational torque or rotational acceleration or anything, any rotational dynamics. None of that has to be considered. And we've got a mass of block B dangling on the other end. And we want to know the largest mass in B for which A begins to slide down the incline. So in other words, you start with no mass, the block A is going to slide down the incline. And you start adding more and more mass until some point where the mass over here plus the friction keeps the block from sliding down the plane. And we want to know what's the largest mass just before you can stop this from moving down the plane. Okay, so let's say MA equals 10 kilograms, theta equals 35 degrees, mu S equals 0.40, and MB is a question mark. Okay. So first, we need to find out what this tension is working in the A direction. Well, let's draw that first. Okay, so we got the incline, angle theta. We have the force of gravity working downward. We have the normal force working upward. We have tension working upward. Here's the real important part. If we want to know just how much may from stopping, from not sliding down the plane, then we must rely on friction working in that direction too. Now, we can find all the components of FG. We can break down the block on an inclined plane and all that stuff. But first, we ought to find out what T tension is. So let's look at block B. Free body diagram, that is FG and T working upward. So the sum of the forces in the y direction is T minus Fg equals MA. And we're going to say, because we're looking at that critical point, the largest mass for which block A still slides down the plane, anything larger, well, what we can do is find the critical point at which it stops block A from sliding down the plane. So at that point, we'll consider acceleration to be 0. And just slightly less than this mass, block A slides down the plane. Okay, so that means T equals F, G equals M sub B times acceleration of gravity. All right, like this. T equals MBG. So now let's come back over to this section, draw our free body diagrams. Okay. So this is FG, friction, T, the normal force, and that's it. And I'm going to draw another free body diagram where I break down all the components. Oh, I forgot to label theta. It's right there. So in this case, I have Fgx, which is equal to Fg, I should probably put F sub A, G. We're looking for the component here, so that's going to be sine of theta. And then down here, F-A-G y is equal to F-A-G cosine of theta. And we still have friction and tension. Oh, and we have the normal force as well. So let's go, as we usually do, and sum up all of our forces. In the x direction, we're calling this the positive direction, so we have T, which equals mbg from above. We have friction, which equals mu s Fn. We have the negative component of gravity, which is negative Fagx, which equals negative Fag sine of theta. In the y direction, we have the normal force, and we have negative Fagy, which equals negative Fag cosine theta. Okay, let's sum up these forces. X equals T plus friction minus Fagx. And that's not moving, so we're setting that equal to 0. If I expand this some more, I can say, what are we after? We're after MB, so we're probably going to have to solve for T. So let's do that. T equals Fagx minus the force of friction. So T, let's expand all these terms. T is equal to mbg. Fagx is equal to negative, Fagx is equal to Fag sine of theta. So Fag is mag sine of theta minus F, which is mu s Fn. So now we have an expression. We don't know what m sub b is, and we don't know what f sub n is, but we can find f sub n. So let's sum up the forces in the y direction. Fn minus Fag cosine theta equals 0 because there is no acceleration in the y direction. So Fn equals Fag, which is just mag cosine theta. So that comes in here. So now mbg equals mag sine theta minus mu sub s mag cosine theta. G's go away. One in every term. So mb equals ma times sine of theta minus mu s cosine of theta. I just pulled the ma out of every term. So mb then is equal to 10 kilograms times sine of 35 degrees minus 0.40 times cosine of 35 degrees. And B then is equal to 2.0 kilograms. Okay. Number 7, a 2 kilogram stone is attached to a string and swung in a circle of radius 0.6 meters on a horizontal and frictionless surface. The stone makes 150 revolutions per minute. The tension then is equal to what? Well, we have a circle, we have a stone, radius r, moving around the circle. The tension in the string is equal to the centripetal force, which is equal to mv squared over r. We have m, we have r, we just need to find v squared. From this, we can find angular velocity, and from that, we can find tension. Well, let's go ahead and put in vt, the tangential speed is equal to r omega, right, squared over r. So this equals mr omega squared. We can put this in terms of omega by noting that in one revolution, there are 2 pi radians, and in 1 minute, there are 60 seconds. So we're left with radians per second. 150 times 2 pi over 60 equals 15.7 radians per second. So then the tension is just equal to 2.0 kilograms times 0.60 meters times 15.7 radians per second quantity squared. So T is equal to 29.6 newtons. I'm sorry. This is not 2 kilograms. This is 0.2 kilograms. But it multiplies out to 29.6. So the calculation there should be correct. All right, question number 8. We've got a guy standing on a horizontal plank. The plank is supported between 2 triangles, 2 supports. Let's draw the free body diagram. We have a support here. I'll call F1. We have one over here. I'll call F2. The plank has weight. Call FG, and then this guy has some weight. We'll call him F3. There's one trick to this problem. It's a very, very sneaky trick. As the guy is walking out towards the edge of the plank, he's getting farther and farther on this side, which is lifting this edge up in a twisting motion about the fulcrum here. So right at the verge of this plank tipping, this equals 0. At the verge of tipping, F1 equals 0. That's because as he walks further out, there's going to be a torque applied to this plank, lifting this end up more and more until this force from the support is going to equal 0 because it's barely touching the plank. All right. So now, once you take care of that, now the problem's fairly simple. We'll just put our axis here. We will sum up the torques. So tau G plus tau 2 minus tau 3 and it's at equilibrium, so they all equal 0. The minus tau 3 comes because this force induces a clockwise torque. So expanding the torque, well, RG FG sine phi g plus R2 F2 sine phi 2 minus R3 F3 sine of phi 3, that equals 0. And this whole term equals 0 because R2 is equal to 0, only because we chose the axis right here. We also know that since this plank is horizontal, all of these angles are 90 degrees, so these all go to 1. So RG FG equals R3 F3. I just moved this term over. And R3 equals RG times FG over F3. Then the question becomes, what is RG? Well, RG is this distance between the center of gravity and the axis. We know this plank is 10 meters long. We know the center of gravity is at 5 meters because it's in the center. And we know this axis is 1 meter from the end. So that means this is 5.0 meters minus 1.0 meters. So that equals 4.0 meters. RG equals. FG is, we're told the weight of the plank is 100 newtons, and the weight of the person is 800 newtons. So R3 is 0.5 meters. Now R3 is really the distance between this point and wherever the guy is standing, F3. It's not the distance. The question says how close to one end can the person stand, but it just so happens that he is at half a meter, which is halfway between this axis point and the end of the plane. So we really solve for this portion. It just happens that this side that the question is asking for is the same distance, half a meter here to here, and it's half a meter from here to here. So he's right in the middle. Okay, this one is quite tricky. We've got a block. This is very similar to the hoisting a crate example problem that we did in class. So we've got a 45 Newton brick that's suspended by a string and dropped, and it pulls a 2 kilogram pulley. So the pulley has weight, and it can be treated as a solid disk, so we have to consider moment of inertia. Let's write down what we have. 0.0 kilograms. I'm going to call little m the mass of the pulley, and the radius of that pulley is 1.5 meters, and big M I'm going to call the mass of the brick. We're not given the mass of the brick, so I'm going to have to take Fg over G, which is 45 newtons over 9.8 meters per second squared. M is equal to 4.6 kilograms. And we know delta theta equals 5.0 radians. So we've got this stuff going on with the pulley and all, but let's look at the block first. In the block we have tension working upward, and we have Fg, I don't know what you want to call it, capital M. So sum up the forces, T minus, the sum of the forces equals T minus Fg capital M. Does it equal 0? Well, no, it's not, because this thing is accelerating, so it's going to equal mass times acceleration. This is, I thought, the trickiest part of this problem, is that since we're working on magnitudes and assigning the negative there, we're going to have to assign this negative here as negative ma, mass times acceleration. So then the tension is just, move this over, it becomes positive, FGM minus MA, which FGM is just, mg, so I'll write it like this. Okay, so we have an expression for T. Now let's go back to this pulley. The tension that's pulling up on the brick is the same tension that's pulling down on the pulley, and that's creating some torque. And the sum of the torque, which is just equal to RT sine of phi, that one force times the one distance, and the angle between them is 90, so we can set that equal to 1. According to Newton's second law for rotation, that is equal to I alpha. So RT is equal to I alpha. Now RT is equal to R times this stuff up here, mg minus A, equals I alpha. And I alpha, we can say, is equal to 1/2 mr squared times alpha, because I for a disk is 1/2 mr squared. All right, so let's bring everything to one side and expand all the terms. Rmg minus R capital Ma, these are capital M's, minus, and I'm bringing this over, 1/2 mr squared alpha equals 0. All right, so you may notice that we have this problem here. We have A and alpha in the same equation. We're going to have to do something about that. So we'll say A is equal to R alpha. Do you remember that? And bring that in for A. And we note that the linear distance this brick drops is equal to the, R times the angular distance that the pulley turns, because they're linked by that string. So Rmg minus Rm R alpha minus 1/2 mr squared alpha equals 0. Well, you'll notice one of these r's cancels from each equation. So mg minus mr alpha minus 1/2 mr alpha equals 0. We can group this some more. Mg minus R alpha is m plus 1/2 m equals 0. Now, if I move this to the other side, divide by a coefficient, and solve for alpha, I'm going to have mg over R times m plus 1/2 m. Well, I shouldn't have put a box around it. We're not done yet. But now we want to know what is the angular speed of the pulley at the end of this acceleration. Well, then we'll just have to go to rotational kinematics. Omega f squared is equal to omega naught squared plus 2 alpha theta minus theta naught, and we'll set theta naught equal to 0. Well, it starts from rest, so that equals 0. So omega final is equal to the square root of 2 alpha theta. Now we can bring alpha in, and that's equal to 2 mg over r m plus 1/2 little m. And don't forget the theta up there. So omega f is equal to the square root of 2 times capital M, which is 4.6 kilograms, times 9.8 meters per second squared, times 5.0 radians, over 1.5 meters times 4.6 kilograms, plus 1/2 times 2.0 kilograms. Omega f then is equal to 7.3 radians per second. There's another way to work this problem. We can use energy considerations. So we look at the work from non-conservative forces, and that is equal to the change in energy, and this is equal to 0 because there are no non-conservative forces here. No friction, nothing like that. So the energy in the beginning equals the energy in the end. But now we have translational energy plus rotational energy to consider. This is in the beginning, and that equals KET plus KER plus PE in the end. We know the object isn't moving at all in the beginning, so we'll just set all kinetic energy equal to 0 in the beginning. And we know the brick is going to hit the floor in the end, or at least it not necessarily hit the floor, but we'll set the final point as a 0 potential energy position. So we'll just say the potential energy in the beginning is going to be converted to translational energy of the brick plus rotational energy of the pulley. Thing to keep in mind here, there's kinetic energy from two different parts of the system. So this is equal to mgh naught. That equals 1/2 capital M V final squared. This is the mass of the brick, plus 1/2 I omega final squared. Well, one thing to note is that we have H. How do we put that in rotational terms? Well, you know that the distance that the pulley rotates is going to be equal to the length of the string that falls out, and we can relate those two things by saying S is equal to r theta. So this distance around the circle is equal to the radius times the angular displacement. So we'll say S is equal to h naught is equal to r theta, and we'll put that in there. What else can we do? Well, this velocity, the velocity of the brick as it's moving downward, is going to be equal to r omega, where omega is the angular velocity of the pulley. So we can put that in as well. V equals, is it V final equals r omega final. And of course, this is the moment of inertia of the pulley. So we can say equals 1/2 little m r squared omega f squared. So let's plug all that stuff in. I don't know why I put that omega there. Okay. Let's start grouping things. I'm going to get rid of this 1/2. I'm going to multiply everything by 2. And so 2mgr theta. And I'm going to move this term over, minus m r omega f squared. Minus because I'm going to move this term over as well. And there's still a 1/2 there. And all that is now equal to 0. Well, you know, there's r times r squared times r squared, so let's get rid of 1r from everything. We can't get rid of the masses because there are two different masses. But 2mg theta minus r omega f squared times m minus r omega f squared times 1/2 little m equals 0. So we're eventually looking for omega f, so I can group these terms together. 2mg theta minus r omega f squared times capital M minus 1/2 little m. Oh wait, hold up. If I'm pulling a negative r omega f from each term, that's going to be then positive, equals 0. So now I'll move this to the other side, solve for omega f. So that's going to equal 2mg. Oh, I made a mistake up here. This potential energy is due to the brick, so that's capital M. Because the brick is the only thing falling. All right. Divide that by the coefficients of omega f, which are r m plus 1/2 m. And we need to take the square root of the whole thing. Compare that to what we had before. 2mg theta, or r m plus 1/2 m, square root of it all. We have the identical solution. Radians per second. So you can work this two different ways. One more problem left. So we have the system as shown at rest, which should make you happy because anything at rest is easier to work with. The force of friction on find the force of friction on the block on the slope. So we note that the weights are the same of these two objects. They're both 20 newtons, and we have B and A. Let's look at this block first. Fg, that's the tension. So the sum of the forces then is equal to T minus Fg, and we know that equals 0 because it's at rest. At rest. There is no acceleration. Equals ma, acceleration equals 0. So then the tension is equal to Fg, which is equal to mg. You know what? I'm going to leave it in terms of Fg because we're given this in terms of weight, 20 newtons. All right, so need to come back to that. Let's look at all the forces. I'm going to draw my diagram first. So there is the force of gravity. There is the tension. There is the normal force. I'll draw the force of friction here. Okay. So we draw our free body diagram. Fg, we know this is theta, this is T, and force of friction is this way, and the normal force is up here. I can then draw another free body diagram where I've broken down everything. So this is force of friction. There's also Fg x, which is Fg sine of theta. We have the tension T, the normal force there, and we have Fgy, which is equal to Fg cosine of theta. Now we have to find theta. That's going to be an issue. Well, we know that the triangle has sides A and B, which we are given quantities for. So we can just say the theta is equal to the inverse tangent of the opposite A over adjacent B, and theta is equal to inverse tangent of 3 meters over 4 meters. So theta is equal to 36.9 degrees. All right, let's go back to our diagrams, though, and sum up our forces in the x direction and the y direction. In the x direction, we have positive tension, we have negative friction, we have negative Fgx. So tension, as we saw before, is equal to Fg. And negative friction is equal to negative mu s Fn. And negative Fgx is equal to negative Fg sine of theta. On the y side, we have the normal force. We have negative Fgy, which is equal to negative Fg cosine theta. And we can go ahead and sum up this y, the y forces. The sum of forces in the y direction equals Fn minus Fg cosine theta equals may, which equals 0 because there is no motion in the vertical direction. So the normal force is just equal to Fg cosine theta. So what about the x direction? Well, the sum of the forces equals positive tension minus friction minus Fgx equals max, and we know that the acceleration in the x direction equals 0. So tension minus friction is minus mu s Fn, minus Fgx is minus Fg sine of theta. I'm sorry, we didn't have to break down the force of friction. It's the problem just ask us what is the force of friction. So I didn't have to break that down any. So the force of friction then is equal to T tension minus Fg sine theta. That's going to be plus Fg sine theta. No, you know what? That is minus. I take it back. Okay, so the force of friction is tension, which is Fg minus Fg sine theta. That equals Fg times 1 minus sine theta. So the force of friction is equal to 20 newtons times 1 minus sine of 36.9 degrees. The force of friction is 8.0 newtons.